So the strength of the intermolecular forces affects the state of the matter at a given temperature. And the strength of those intermolecular forces depends on the particles themselves, their structure. So if we have strong intermolecular forces, then we're going to have higher melting points and higher boiling points. I sometimes think of intermolecular forces as being a bit like Velcro. So if you imagine a bunch of people wearing Velcro suits, right? And so it's got those little grabby, prickly things on it. And as you move past another person, as you brush against them, you kind of stick to them, right? Because the Velcro is sticky. So if the Velcro is really sticky, you could get stuck to the people around you. And then everybody's just stuck and nobody can move, right? You're wiggling, trying to get free, but you can't get loose. That's a solid. If the forces are not as strong, then you might be a liquid. And so you can slide past each other, but you can't quite break away from your neighbors, but you can slide past. These intermolecular forces, well, let me go back to that. So when a solid melts, what happens is the particles have enough vibrational motion that they can break loose from the particles next to them. So that's like the people that are just in this Velcroed mass, right? They're moving back and forth and they manage to break free from the person next to them. Then they move over and they get stuck to the person over there. But if they have enough energy, if they're vigorous enough, they can keep moving around like that. So that would be melting. Boiling is when the particles have enough energy that they can completely break free from the other molecules. So if the Velcro is strong, then you need a lot more energy to break loose. Does that make sense? So high melting point means strong intermolecular forces. Low boiling point means weak intermolecular forces. Okay? Those intermolecular forces come about because of charges, electrical charges. Some of these are permanent, some of them are temporary. Some of the charges are like +1, +2, etc. Some of them are just partial charges, not actually ions, but just a little bit of a charge. So Coulomb's law helps us to understand the relationship here. So E is energy, the potential energy of two oppositely charged particles, Q1 and Q2. So those are the charges on the particles. And R is the distance between the two particles. This is just a constant, and we can kind of ignore that. So what I'd like you to be able to remember is that the energy is proportional to Q1 times Q2 over R. In order for this to be an attractive force, the energy needs to be negative, and so one of these charges must be positive and one must be negative. If they're both positive or they're both negative, then the energy is positive, and that's a pushing away, a repelling. Okay? R is the distance between the two particles. So let's think about your refrigerator, and you've got some papers that you need to stick up there so that you don't forget. And so you take a magnet and you stick the paper to the refrigerator, right? And it hangs there, right? Then you realize, oh wait, I have another piece of paper. And so you stick another piece of paper under the magnet. And you keep doing that. You keep adding a piece of paper. What happens eventually? The whole thing starts sliding down, right? Because the magnet now is not as strongly attracted to the refrigerator. And all that's different is you added a sheet or two of paper. Very small difference in the distance between the magnet and the refrigerator. But it affects the attractive force between those two objects. And then gravity's pulling down on the paper, and so the whole thing slides down the refrigerator. Now, if you took the same amount of paper and took a stronger magnet, it would hold just fine, because the attraction between the magnet and the refrigerator depends on the strength of the magnet and on the distance. So the greater the distance between the two objects, the less attraction. The greater the charges on the objects, the greater the attraction. Does that make sense? So if we can remember this concept, then we can reason out a lot of the relationships that we'll be seeing. So we talked about bonding, probably talked more about bonding than you'd like, right? Bonding forces have large charges at very close distances. So here we have a water molecule, and there's a covalent bond between the oxygen and the hydrogen. There's a shared pair of electrons in there. We have large charges at very close distances. The distance between the two nuclei there is 96 picometers. Intermolecular forces occur between one molecule and a neighboring molecule, so obviously that has to be a larger distance. Here it's about 300 picometers, so 3 times the distance. So then the force of attraction, if the charges are the same, will be 1/3, right, as great. So the intermolecular forces are much weaker than actual bonding forces. So what are these forces? We're going to talk about 4 different kinds of forces. They're all attractions between oppositely charged particles. So the dispersion force, this also has a bunch of other names. London forces, van der Waals forces, induced dipole forces, lots of different names. I'm going to try to stick to dispersion force because that's what your book uses. So all particles, molecules and atoms, have dispersion forces. So what happens here is you have fluctuations in the electron density. So here we have, anybody know what what atom that is? How many electrons does it have? It's helium. It's got 2 electrons, right? So here we have helium. And we talked about what these electrons are doing. The electrons really are in standing waves around the nucleus, but they can also act like particles. And so if you would take a snapshot of them, you lose the whole blurring effect of the standing wave, and you could see, oh, well, it's here and here. So we're taking a snapshot of the electrons. And at another time, you take a snapshot, and they're over here. And another time, they might be both over on this side. So they're not always completely evenly spaced out at any given instant. Does that make sense? I think of this a little bit like people on a boat. When my husband and I were on our honeymoon, we went to San Francisco and we took one of those blue and white cruises out in the San Francisco Bay. We had a whole bunch of tourists, and they're all standing on the deck of the ship and looking at stuff, right? And there's no assigned seats. There aren't any seats. You're just walking around. So you're walking around, and sometimes it could happen that you get a whole bunch of people on one side of the boat. Now, hopefully they haven't overloaded the boat, but you can imagine that it might cause the boat to tilt just a tiny bit, right? So that if you had like a marble on the floor, it would roll just a little bit. So just like the people on the boat at any given instant, the electrons can be unbalanced. They might be unevenly distributed. This also reminds me of a time when I walked into the living room and all 6 of my children were piled together on half of the couch. Very, very strange. So strange I took a picture, and I don't think it's ever happened again. Usually they're spread out, and now they're spread out sometimes all over the world. But at that instant, they happen to be, just randomly, all together, piled on top of each other. So the electrons can do that as well. They are independent, And so they're just, out there, and at any given instant, you could have, in this helium atom, the two electrons on one side of the nucleus. So here we have both of the negative charges. There's no negative charge over here at all, but the nucleus is positive. So then if we look at the whole atom, we'd see that this side of the atom is a little bit negative, and the other side of the atom is a little bit positive. Does that make sense? It's lopsided. When one atom becomes lopsided, it can induce lopsidedness in a neighboring atom. So here's our spontaneously lopsided atom. The electrons are both over here, and this side is positive. Now this neighboring atom, the electrons are attracted to the positive side of this atom. And so that induces a dipole in the next atom. A dipole is a separation of charge, where you have one end that's positive and one that's negative. So this is a spontaneous or an instantaneous dipole. It's temporary, and it can induce a temporary dipole in the neighboring atom. And then that one can do the same over here. So if we're talking about the cruises on the San Francisco Bay, it's a little bit like the ship was going past Alcatraz, right? And Alcatraz is what people wanted to see, and so everybody crowds to that side of the boat, right? Now the boat's starting to tip, and then there's a boat nearby, and the people are like, ooh, that boat's going to capsize, and so everybody goes to the side of the boat to watch this other boat tip over, right? So it's this sort of a chain reaction. Does that make sense? So this type of thing occurs between all particles, all atoms, all molecules. Everything does this, because everything has electrons. Now, is this force very strong? No. It's very weak, because this is not an ion. This is a partial negative charge. It might be like 1/10 of a -1 and 1/10 of a +1. So that's a much smaller charge than an actual ion. The strength of the attraction depends on the magnitude of the charges. So if the charges are tiny, then the attraction is tiny. It also depends on the distance between the particles. But the thing about small forces like this is if you have enough of them, they are significant. So if you think about getting hit by a raindrop, you're like, oh, yeah, a little wet spot on my skin, no big deal, right? But if you have 1 million raindrops land on you, each of them is a tiny little thing, but now you're drenched, right? Because a lot of little things is significant. So with these instantaneous dipoles, they come and they go. They're only there for a fraction of a second. They're not very strong, but they keep happening, and they're happening all over the place. Okay? So what affects the strength of these dispersion forces? Well, a big effect is how easily the electrons are polarized. So how easy is it for this electron cloud to get lopsided? And this correlates with atomic mass, because when we have a larger electron cloud, it's easier to polarize because the electrons in those higher energy levels are farther away from the nucleus. And so they're more loosely held. I think of these larger atoms like xenon as just being kind of large and flabby, right? They're big and flabby, and then here's helium, and he's little and he's just really tight and firm. I don't know why I think that, but So this is flabby, and the electron cloud can get pushed around very easily, okay? So it's more easy to polarize, and so more easy to polarize means this is going to have stronger dispersion forces than the smaller atoms. We can see the effect of this on the boiling points of these noble gases. So going from helium down to xenon, the boiling point changes from 4 Kelvin to 165 Kelvin. So what's holding these xenon particles as a liquid at very cold temperatures must be stronger than what's holding helium, because the temperature is a measure of how much kinetic energy the particles have. So at 4 Kelvin, helium atoms have enough energy to break loose and the liquid will boil. For xenon atoms, you have to raise the temperature significantly higher to 165 Kelvin. That make sense? Shape of the molecule also has an effect. Of course, atoms are all spherical, so there's no shape effects for the atoms, but for a molecule there is. So here we have 2 variations of pentane. Pentane has 5 carbon atoms, and those carbon atoms can be in a line, or you can have 1 carbon in the center with 4 carbons bonded to it, and so this molecule is going to be more spherical in shape. This is going to be more linear. And so here we have space-filling model illustrations of these. So in order for intermolecular forces to occur, the particles have to be able to get close to each other, and surface area starts to play a part. So this is where the Velcro analogy works really well. If you have these 2 things covered in Velcro, they can interact with this large area between them. And the more area you have with the Velcro, the stronger it holds, right? So if you have a little dot of Velcro, like maybe on your shoe or a pocket, it's easy to take it off. But if you play on one of those inflatable things where you put the Velcro suit on and you jump against the wall, it will hold your entire body weight stuck to the Velcro wall, because large surface area, right? If you just stuck your elbow up there, would you stick to the wall? No, you'd fall right off. So more surface area, more stickiness. Over here, these are spherical shapes. They can only touch each other at one point. Very small area. So these are not very sticky to each other. So which of these do you think is going to have a higher boiling point? Higher boiling point means it takes more energy to break loose. So higher boiling point, stronger forces. So we would expect this one to have the higher boiling point. And sure enough, that one boils at 36 degrees Celsius. This one boils at 9. Because the particles are not as attracted to each other. That make sense? Yeah.
So, in the picture where they look like that, that's a representation of the first one?
Mm-hmm.
No, it's the representation of the second one?
Yeah, so this, we like to compare these 2 because they have the same chemical formulas. Their mass is the same, right? What's different is the shape.
Yeah. I just was making sure that, they weren't all 4 different, in this drawing.
No, this is the same as these.
Okay, yeah.
And this one, yeah, good to ask. This is the same as these. They're just sort of emphasizing the spherical shape here. Yeah. This graph is showing boiling point versus molar mass. These are called normal alkanes. They're all just straight chains. And so here we see the effect of increasing mass. So as the mass of these gets larger, they're more polarizable. But also here we have an effect because these are getting longer and longer. They have larger surface area. This one has more surface area to stick to its neighbor than the hexane does. And so it'll have a higher boiling point. So that's dispersion forces. And we have dipole-dipole forces. Dipole-dipole forces are found in polar molecules. So this is why we're talking about this after we've talked about molecular shapes, because we have to be able to understand what makes a molecule polar before we can talk about this. So these forces are stronger than dispersion forces because they are always present. Dispersion forces come and go, whereas the dipole-dipole forces are permanent. They're always there. So here we have an illustration of, I guess, dimethyl ether. It doesn't actually matter, does it? This is a polar molecule. Here's this oxygen is always slightly negative, and the hydrogen end over here is always slightly positive. And so the negative end of one molecule will be attracted to the positive end of a neighboring molecule. And that's an attraction that's always there. It doesn't come and go. So the magnitude of those charges is always the same. What can change is the distance between them. And this is the same molecule, just with looking at the electron density. And so we see there's more electrons here, and that's attracted to this part over there. So polar molecules have dipole-dipole forces. This is in addition to dispersion forces. And so we see that polar molecules have higher melting and boiling points than nonpolar molecules of similar size. So here we're going to compare formaldehyde and ethane. Their molar masses are almost identical. So here's their structures. For ethane, we see that there's 2 carbons in the middle and hydrogens around. And I've asked you to remember that a carbon-hydrogen bond is considered a nonpolar bond. So if all of the bonds are nonpolar, the molecule must be nonpolar. There's got to be something that's polar in order for the molecule to be polar. Over here, we have an oxygen-carbon bond, and so that's going to be a polar bond. Then we can think about molecular shape and predict that this is a polar molecule. It's got a negative end and a positive end. So if we look at the boiling point, this boils at minus 19. The other one boils at minus 88. So this is a much lower boiling point. That tells us that the forces that are holding these pieces together as a liquid are weaker than the ones holding these molecules together. Does that make sense? Here's another graph comparing boiling points. Here we're looking at dipole moment, so that's a measure of how polar are these molecules. And we've chosen 5 different compounds here that are similar in size. Because if we compare something that has a very large molar mass to something with a small molar mass, then we could have dispersion force strength become a factor as well. Because these are all roughly the same size, then we don't have to worry about dispersion forces. All we're seeing is a difference in the strength of the dipole-dipole force. So we see that as the dipole moment increases, the boiling point increases. So here's acetonitrile, boils at 350 Kelvin, whereas propane boils at, what is that? Maybe 230 Kelvin. So propane is a gas at room temperature, acetonitrile is a liquid. Its dipole-dipole forces are stronger. So polarity is important in determining miscibility. So that's a word that doesn't show up in everyday life. This is not a word, but it probably makes more sense. Mixability, right? Mixability, miscibility. Miscibility is the ability of 2 liquids to mix. Okay, so water and alcohol are miscible. Water and oil are not miscible. They don't mix, they separate into layers. In this picture we have pentane and water. The pentane is nonpolar, the water is polar. The water molecules are attracted with the dipole-dipole forces. pentane molecules only have dispersion forces. So their forces of attraction are weaker. Because the water molecules are so attracted to each other, they will squeeze together and push out the pentane. They won't let it in. And the pentane is just sort of excluded. The reason the pentane sits on top is because it's less dense. You can also have a nonpolar liquid that is more dense than water, and the water will sit on top and squeeze the other into a layer below it. So we have this phrase, like dissolves like, that helps us to predict whether things will dissolve, whether things will mix with each other. So if the intermolecular forces are alike, then they will probably mix. If they are not, it will not mix. So here we have two substances that are not alike, and so they do not mix. Polar and nonpolar don't mix. So we should be able to answer questions like this. Which molecules have dipole-dipole forces? First, we have to recognize what kind of molecules have dipole-dipole forces. Polar molecules. So we need to identify if these are polar. If they're polar, they have dipole-dipole forces. If they're nonpolar, they don't. So the first one is carbon tetraiodide, and I wrote the name out because sometimes that looks like Cl4, which is not a thing. How do we predict if this is polar? Well, the simplest way, which works most of the time, draw the Lewis structure. So Lewis structure for this, you're going to have a carbon, and you're going to have the iodines around, and then you can count up all the electrons and everything. There will be lone pairs around the iodines, but there's no lone pairs on the carbon. The carbon has 4 bonds, that's its octet. So we can look at this molecule and say, well, there are no lone pairs on the central atom, and all of the atoms that are bonded to it are the same. This is a beautiful symmetrical molecule, right? This is nonpolar. So this is a nonpolar molecule. Whoops. No dipole-dipole forces. Because there isn't a positive and a negative end of this molecule. Carbon tetraiodide would just be held together by dispersion forces, random fluctuations. CH3Cl. So if we draw the Lewis structure for this one, and there'd be lone pairs around there. Is that molecule polar? Yeah, it is. So there aren't any lone pairs on the central atom. What that tells us is that these bonds are evenly distributed in space. So the bonds are symmetrical. But one of these is bonded to chlorine, and the others are bonds with hydrogen. The chlorine is different. It has a different electronegativity than hydrogen. And so chlorine being more electronegative is going to pull the electron density away from the rest of the molecule. It's lopsided, it's not perfectly symmetrical. So this one's polar. Why did I do that? Polar. So yes, it has dipole-dipole forces. How about HCl? Is there a central atom? No. But there's only one bond. Is it a polar bond? Do hydrogen and chlorine have different electronegativities? Yeah, they do. So, rule of thumb again, when you're predicting if a bond is polar or nonpolar, are the two elements the same? No. Then it's polar. There are situations where you can have two different elements and it'll be a nonpolar bond, but those are very unusual except for carbon-hydrogen. So carbon-hydrogen bonds are nonpolar, but this is not carbon-hydrogen, this is hydrogen and chlorine. The bond is polar, so the molecule's polar.
So because they're two different, you said something about it being different that makes them polar?
Yes.
Yeah.
So electronegativity is the ability of an atom to draw electrons to itself. So there's a pair of electrons being shared here between hydrogen and chlorine. The chlorine is hogging them, is pulling them. They're spending more time over here, and so the chlorine end of the molecule is a little bit negative, and the hydrogen end is a little bit positive. There's an uneven electron distribution. If you had like a nitrogen molecule. So there's only two things there, a triple bond in between. But these two atoms are the same kind of element. So one is not stronger than the other in terms of pulling electrons. So the electrons in this bond are going to be shared equally. This is a nonpolar molecule. It's not going to have a positive end or a negative end.
But because the chlorine, so the two nitrogen, that's nonpolar?
This is nonpolar.
But the hydrogen and the chlorine are polar.
Mm-hmm.
Because the chlorine's on the other.
Yep. So that's nonpolar, and this one's polar. So just, very broadly, a nonpolar molecule is symmetrical. There's not a positive end, a negative end. You look at it, and it's just like, a ball, right? Polar molecules are lopsided for one reason or another. This one's lopsided because this atom is different. You can also have things be lopsided, like ammonia. So ammonia has 3 hydrogens bonded to nitrogen, but nitrogen has a lone pair. And so when we look at the distribution of those electron groups, they are distributed symmetrically around the nitrogen atom, but one of those electron groups doesn't have a hydrogen. And so it's going to be a lopsided molecule that's going to be polar. Any questions? Right. Just because this one doesn't have a central atom does not mean that it's nonpolar. So if you have a diatomic molecule, 2 atoms, it will be polar if the bond is polar. If the bond is nonpolar, then the molecule's nonpolar. For more complicated molecules, you can look at the Lewis structure. If you see a lone pair on the central atom, you're done. It's polar. Very, very few exceptions. If there's no lone pairs, then you have to look at, well, what's bonded here? Are those things the same? Like up here? These are all the same. This is symmetrical. Nothing stronger or weaker in terms of pulling electrons around. But here we've got one that's different. And so we would predict that this is a polar molecule. So there are a lot more details to predicting polarity, but what I want you to understand is the broad ideas, right? We don't have to sketch out the exact molecular shape, the geometry. We don't have to add up all the different dipole moments on all of the bonds. That can be done, but you don't have to do that to predict whether it's polar or nonpolar. Third type of intermolecular force is called hydrogen bonding. Hydrogen bonding is really just dipole-dipole forces that are really strong. So they've been using steroids or something. Super dipole-dipole force. So it happens between polar molecules, but it's polar molecules where we have an especially large dipole. And so we're going to see this when we have hydrogen that's bonded to fluorine, oxygen, or nitrogen. And what's special about these three elements is that they are the most electronegative elements, and they are also very small. What's important about them being small is with the small atom, the molecules can get closer together. If you have a large atom, like chlorine is also very electronegative, but it's significantly larger than fluorine. And so then you have this larger distance between the particles, and so the force of attraction is less. It's Coulomb's law. So these are important because they're small. So we need to remember fluorine, oxygen, and nitrogen. So for hydrogen bonding, you've got a polar molecule with fluorine, oxygen, or nitrogen bonded to hydrogen. You guys seen or at least heard of the movie E.T.? What did E.T. say? E.T. phone home, right? Phone home. Phone home. Okay? F-O-N bonded to hydrogen. You're welcome. So here we have, I think this is hydrogen fluoride down here. Here's the fluorine, here's the hydrogen. Hydrogen is also very small and it's not very electronegative. So we have stronger dipole here. So these partial charges are larger than in most molecules. And because they're small, they can get close together. And so we have this attraction between the negative end of one and the positive end of the other. Common misconception, hydrogen bonding is not a hydrogen-hydrogen bond or a hydrogen-nitrogen bond. This is the hydrogen bond. It's the attraction of opposite charges between two molecules. It's not inside the bond. I'm sorry, it's not inside the molecule. So if you look at something like methane, methane has covalent bonds between hydrogen and carbon. Those are not hydrogen bonds. This doesn't do hydrogen bonding because it's not a polar molecule and it doesn't have fluorine, oxygen, or nitrogen bonded to hydrogen. So here we've got hydrogen bonding in ethanol and in water. So ethanol, here we have oxygen bonded to hydrogen. So this is an especially strong dipole. And because the small size of the oxygen, then this hydrogen can get closer. And the attraction between the hydrogen on this molecule and the oxygen on the other molecule, that's the hydrogen bond. This also happens in water. When you look at the formula for water, H2O, and you begin to draw a Lewis structure, typically we'll start drawing it like that, and you might say, oh, well, that's symmetrical, that's nonpolar. But, oh, let's use the big ones. There's two lone pairs on the oxygen. So when we look at the full Lewis structure for water, we see two lone pairs on the central atom, done, polar molecule. It's going to be lopsided. It's going to have hydrogen bonding because we have oxygen bonded directly to hydrogen. ET phone home. Fluorine, oxygen, or nitrogen bonded to hydrogen. And so the hydrogen bond is this attraction between the oxygen on one molecule and the hydrogen on another molecule. It really is a dipole-dipole force. It's got a special name because it's extra strong. Any questions? Hydrogen bonds are between molecules. Chemical bonds, like covalent bonds, are between atoms within the same molecule. Okay, so hydrogen bonds are not covalent bonds. Hydrogen bonds are significantly weaker than covalent bonds. They're only like 2 to 5% as strong, so much, much weaker. We observe that compounds with hydrogen bonds, because hydrogen bonds are stronger, they have higher melting and boiling points. So here we can compare ethanol and dimethyl ether. Same chemical formulas, same molar mass, but this one is polar. They're both polar, but this one does not have it doesn't have oxygen-hydrogen bonds. So we really need the to look at how these are connected. So in ethanol, we have this oxygen-hydrogen bond. In dimethyl ether, there's oxygen and hydrogen present, but the oxygen is not bonded to hydrogen. There's lone pairs there. Both of these are polar, but this one does not have hydrogen bonding. Okay, so then we look over here at the boiling point. Ethanol boils at 78 degrees Celsius. That's pretty hot. Dimethyl ether boils at minus 22. So at room temperature, ethanol is a liquid, dimethyl ether is a gas. The difference in the boiling points here is just due to the hydrogen bonding. Any questions? This graph is showing boiling point versus molar mass, and here we're looking at compounds between group 6A elements and hydrogen and group 4A elements and hydrogen. So for group 6, we see a fairly good trend here that as you go higher in molar mass, the boiling point gets larger. And for group 4, these are all going to be polar because they're going to have lone pairs. So overall, their boiling points are higher. But again, we see this increase. But who is totally messing this up? Water, oxygen. We would expect this to be down around here, or if there's a dip like this, maybe even down here, around minus 75 or so, but its actual boiling point is 100 degrees Celsius because of hydrogen bonding. Hydrogen bonding causes the water molecules to stick together very, very strongly. So you have to increase the temperature, get them really, really agitated before they will boil. Hydrogen bonding is super important. Hydrogen bonding is the reason we have liquid water. The planet would be very, very different without hydrogen bonding because all the water would be in the gas state. We should be able to answer questions like this: which has the higher boiling point, HF or HCl, and why? Of course, why is the hard part, right? So, looking at boiling points or melting points, we're looking at strength of intermolecular forces. So we have to identify what kind of intermolecular forces, and that depends on whether these are polar or nonpolar. So both of these are diatomic elements. Diatomic molecules, right? Just two atoms. Is HF polar? Yes, it is. So that's polar. Is HCl polar? Yep. Those are both polar. Because we've got two different elements here. So I expect you to tell me those are polar. Does HCl have hydrogen bonding? No. Phone home. FONH. There's no fluorine, oxygen, or nitrogen. Does HF have hydrogen bonding? Yes, it does. So, because it's polar, we have dipole-dipole forces. And we've got hydrogen bonds. The HCl is just dipole-dipole. Stronger attraction, higher boiling point. So HF has a higher boiling point, because it has hydrogen bonding in addition to dipole-dipole forces. Okay? The fourth force technically is not an intermolecular force because it's not between molecules. It's between a molecule and an ion. It's called the Ion-Dipole Force. And this happens when you have an ionic compound mixed with a polar compound like water. So this is really important in aqueous solutions of ionic compounds. It's the strongest type of intermolecular force because here, instead of partial charges, this chlorine has a full -1 charge. Even with hydrogen bonding, you don't have a full negative charge. You might have, minus 0.2 or something like that. Part of the strength of the hydrogen bond is that they can get close together because the atoms are small. So here we have a polar compound like water and an ion. So the chloride ion is attracted to the positive ends of the water molecules. The other part of this ionic compound, the sodium, is positively charged, and it's attracted to the negative sides of the water molecules. And so the attraction between the ion and the dipole in the polar compound is the Ion-Dipole Force. And that is stronger than hydrogen bonding. And this is responsible for the formation of aqueous solutions of ionic compounds. So this table from your textbook gives you a nice overview of the 4 different types of intermolecular forces. It's important to know their names, be able to identify which of these are present in a given molecule. And so here, everything has dispersion forces. Polar molecules have dipole-dipole forces. For hydrogen bonding, you've got to have hydrogen bonded to F, O, or N, phone, home. Ion-dipole, you've got a polar compound with an ionic compound. And the strength increases as you go down. Hydrogen bonding is responsible for the shape of your DNA. So, DNA has 2 strands, and those strands are held together by hydrogen bonds. DNA is composed of a glycophosphate backbone, and then on that chain, almost like charms, you have these different bases hanging off of them, and there's 4. There's thymine, adenine, cytosine, and guanine. And because of the shapes of these bases, thymine and adenine can form 2 hydrogen bonds with each other. They go together very well. They just link up beautifully. Cytosine and guanine can form 3 bonds with hydrogen bonds. And so they're gonna just snap together. They go together like a hand in a glove, right? So cytosine and guanine always pair together. Thymine and adenine always pair together. So in a strand of DNA, on one strand you'll have an A, and on the other strand you'll have a T, and they'll be stuck together with hydrogen bonds. If one has a G, the other has a C, and they stick together that way. And then your body is able to make more DNA by taking these old strands apart, separating them, and then using the original strand as a template to make a new one. And so your ribosomes bring in, here's a T, it'll bring in an A, and then it'll zip it together with this backbone. And over here on this A T is going to come in. And here for the G, a C is going to come in. And it'll match them up like this. And so the complementary strands in the original DNA are now duplicated, and you have 2 new strands from the one. That makes sense?